Okay, so we just generated this graph. We wrote the equation for it, which we found that the slope was the spring constant. Now we're going to look at something a little bit different about this graph. All graphs have a physical meaning about the slope. The slope means something. And in this case, the physical meaning of this slope is that it represents how resistive that spring is. It's called the spring constant, which I explained in the previous video. However, there's another thing that often has a physical meaning, and that is the area under the curve, which we have done several times. We've done area under the curve in motion studies and things like that. But we're going to look at it in a slightly different way, in a slightly different graph. So if I come up here and click the integral button right here, integral is basically just a fancy calculus way of saying area under the curve. So I click this, and it's going to do a nice job of showing me what area I'm actually calculating here. And so if you look at that, oh my goodness, that is a beautiful looking triangle. You're right, it is. So let's just go back here and let's make a list of an equation for the area of a triangle. So we know that area of a triangle is 1/2, which I'm just going to put 0.5, times base times height. We know that. So then if I say, well, the area in this case is equal to 0.5 times, and if I look at my graph again, my base would be whatever my spring displacement is down here, spring displacement, x, and my height would be whatever my force is. So I'm going to say that the equation for the area of this graph is going to be equal to the spring displacement times the force. So that's it. And so let's just do this real quick. Let's just figure out the total amount of area in this graph by plugging in numbers. So I know that the maximum displacement that I have by looking at the table over here is 0.5 and the maximum force is 100. So I'm just going to plug those numbers into that equation. So then I'm going to say area is equal to 0.5 times the spring displacement was 0.5 meters times 100 newtons. And so when I do that, I'm going to get the area to be equal to, well, half of 100 is 0.5, or half of 100 is 50, and 50 times 0.5 is 25. So therefore, we have an area of 25. And then the question becomes the units. Well, this is the beauty, folks. When you take newtons times meters, it's something. It's weird, but it's something. We've never seen this unit before. The question is, what is a Newton meter? Well, let's just Google it, shall we? What is a Newton meter? A Newton meter is not what I was expecting. Here we go. A Newton meter is, what is that? A joule? Oh my goodness, a joule, not the Joule Pods, folks. It's not the Joule Pods, folks. It is a joule, which is a measurement of something that you have seen before. A joule, so this is, in other words, an area is equal to 25 joules. A joule was talked about in chemistry when you talked about the amount of energy that was either entering or leaving the system. A joule is a measurement of energy, folks. Wait a minute. So if the area of this triangle is energy, what type of energy is it? Oh my goodness, folks. We looked at springs. I bet that's the amount of energy that's stored in the spring. And in fact, it is. This is another way of writing the area equation. The elastic energy of a spring is equal to half of the spring displacement times the force. Now, another way of writing this equation is just simply substituting in this. So we know that the force of the spring is equal to K times X. And so this is one equation right here, but another equation that they often write is EEL is equal to 0.5 times X times, now I'm going to substitute what I know a force is, which is K times X. And so then that simplifies to EEL is equal to 0.5 times K times X to the second power. In other words, squared. And that's it, folks. The area under the curve is the elastic energy.